Okay, so next up we have Alexander. He will be speaking about UEFI and especially in U-Boot. So, big round of applause please and enjoy the talk.
Good afternoon. You can all hear me, I guess, right? Just fine? Perfect. So this talk is going to be about running UEFI applications in U-Boot. I could have just as well called it YaBits, because it really is basically the same concept just inside of U-Boot with less drivers, but I'm going to get to that. So who am I? My name is Alexander Graf, usually go by Alex. My official role is a KVM and QEMU developer at SUSE, so I really have a big virtualization background. I usually work in virtual systems rather than physical ones. But a couple years back, we saw a small team at SUSE basically saw that ARM is evolving into fields where an enterprise distribution might be useful too eventually. So we started founding the SUSE ARM team and started to ignite running SUSE, OpenSUSE, and even our enterprise distribution now on ARM systems. And as part of that, I basically started writing the U-Boot UEFI implementation that this talk is about, and I ended up becoming the Raspberry Pi maintainer in U-Boot. Woo. Because guess what? It's the biggest enterprise server platform we have on ARM. No, the biggest volume, but that's the different story. I'm not going to get into details. This actually was true. So why do we want UEFI? If you look at how systems boot, and this is really looking at the embedded sphere mostly, if you're looking at how an embedded system boots, you usually have a boot ROM, and that comes from your silicon vendor. So you have a small piece of code that nobody can change after the chip went out, and that just does some magic, and then you need to do more magic to actually get the system up and working. And if you think of it as a traditional embedded developer, that magic is everything you do, and then you do more magic and even more magic, and basically that's what you call firmware, and then you deliver it, and everybody's happy. Well, it turns out life is not as easy. It might have been that way back in the 80s. These days, firmware is way more complicated. Firmware includes a lot of different components. Firmware includes, for example, usually a bootloader like U-Boot. Firmware includes a description of what your hardware looks like, which we usually deliver as device tree in the ARM world. It includes an operating system, which in most cases is Linux, and even a tool stack on top of that operating system with lots of different libraries and sets to do things like updates, etc. And of course, you always want to run an application that is running on your inside of your firmware to do things, because just running an operating system is pretty boring to most people that don't work for SUSE or something. Now, what that means is that the system just basically becomes so complex that the only way to deal with it realistically is by splitting up tasks into different tenants. And different tenants in our world means that ideally you want to have everything that's related to initial boot get delivered by somebody who actually knows the hardware. Because, well, the whole task of the booting process is to initialize hardware or the biggest task of it is to initialize hardware and to expose a sane state of hardware to you, and then expose the description of what that hardware looks like to you. So you want to have somebody who's close to that hardware get you that description, and that could even be in-house. It could just be a different department that basically works on hardware. You may want to have the operating system from a vendor like us. You may want to have the operating system done by yourself, by somebody else, but you do want to treat the operating system as some opaque blob in most cases. It's what people do already with Yocto recipes that they just copy off the internet and hope they're secure. And then you usually end up giving application development tasks to one person, a group of people, maybe even different companies, because you happen to have 10 different applications running on your embedded system. And through each of these components, you have requirements on basically transitioning phases. Right? So you have some agreements between the boot ROM and your bootloader, because the bootloader needs to know how it gets invoked. You want to have some agreement, some treaty between your firmware and your operating system, so the operating system is always aware on how it gets booted and how the whole handshake works. And the same thing goes for user space. I mean, this layer is pretty obvious to most people who work on Linux. That's the syscall interface and a couple of user space interfaces like dbus that just became a de facto standard. But if we had this presentation 20 years or 30 years back, people would have argued about that interface already, right? Now, if we're talking about these interfaces and standards of interfaces, I can keep thinking of this comic, and as most of you know, XKCD. If we invent standards, that means we're adding standards. We don't replace standards, we only add to them. So the best way to deal with existing interfaces is by adopting them and not creating alternatives to them, because once you do an alternative, it means it's going to stick forever. And you won't replace the old ones usually. And in our world, that really is UEFI. The server business is going UEFI throughout. Every ARM server you can buy these days is UEFI enabled. Pretty much every x86 system you can buy these days is UEFI enabled. So in an ARM ecosystem, for us, it made the most sense to, instead of enabling both a U-boot specific way of booting and a server specific way of booting, to just enable one and be done. And the idea was to basically just teach the systems that are around, the U-boot in this case, to teach the boot layers that are already around how UEFI works. And that basically gets me down to what is UEFI. So who of you knows what UEFI means? Not the abbreviation. I mean, the abbreviation is just a unified extensible firmware interface. But what does that actually mean? Who thinks this is the 5 megabyte blob that you're running when you're booting your operating system? Who thinks this is EDK2 or Tiano Core? Who thinks this is just a PDF document that describes interfaces? This is an amazing audience. Usually you wouldn't get that answer. So yes, UEFI is just a specification that tells you how to talk to firmware, but there's almost no correlation, I'm saying almost because that was in detail, between the implementation and the actual specification, right? You can easily implement UEFI using Tiano Core. You can just grab Tiano Core off GitHub and build it, and you basically have a valid and working UEFI implementation. Or you could go and build U-boot, and you have another working UEFI implementation that has nothing to do almost with that other Tiano Core, with the Tiano Core implementation, except for the fact that, well, they're both open source and they both run the same code as downstream code, but not they don't actually share code. There are a couple of reasons for that. The biggest reason for me personally is the coding style. If you've ever tried to read EDK2 code or any Windows code for that matter, my eyes start bleed. This is a really good example because that one is actually readable. This is just a small excerpt from a function out of EDK2 code, really. This is what EDK2 code looks like. You can see all the uppercaseness, all the camel caseness, everything that basically makes up Windows style, or in that case, EDK2 style code. Whereas U-boot code is written in essentially Linux coding style. There are a couple of caveats, but it basically looks like a normal Linux environmental piece rather than an alien. Right? And this is the same function, basically. And most of the pieces really wouldn't be necessary if we had done a couple of decisions differently. The only reason we have the EFI entry and EFI exit is because we need to swap one register when entering and exiting functions, because our internal calling ABI is different from the official EFI calling ABI. And that EFI API thing on the top, we only need because of x86 64, because again, they decided to use a different ABI than everybody else. Well, no. A different ABI except for Windows than everybody else. Say again? This is what auto-generates the trampoline. So if you look at Tiano Core code, imagine you have two pieces of code that are trying to call each other. How do they call each other? What would you traditionally do? You usually would have one file just call, or one function call another function, right? And that's not how the thinking of a Tiano Core world works. The thinking is that you basically go through a broker somewhere in the core, UEFI core, to find a protocol, to find a pointer to some reference in that protocol, and then you find the function pointer, and then you can eventually link yourself somehow into calling the actual function you wanted to call. But everything's very explicit, to put it in mild words there. The idea is very simple, or the rationale behind it. The rationale is that it basically allows you to create very nice black boxes. So it allows you to create silos and different departments or teams that create different pieces of code that basically just work by contracts and obligations. So you have a spec and it works against the spec, or if it doesn't work against the spec, it's their problem and not yours. It obviously also allows for really nice replacement of, it allows you to implement parts of it as closed source, of course, which, again, are all reasons we don't care. These are all reasons that we don't care about in a U-boot environment, because in U-boot what happens is if one piece of code wants to call another piece of code, that piece of code calls the other piece of code and you're done. Right? It's one monolithic block, similar to how Linux works, in that you really just link and you're done. So looking at those two, there's one more reason U-boot is interesting to us as an alternative to EDK2 or Tiano Core, and that's hardware support. So if you look at what Tiano Core supports in its core, it really is very core. Basically, it supports running on an emulated platform and an outdated one. There are a couple of platforms around that you can basically clone one GitHub repo for the core and another GitHub repo for board enablement, and then you can merge those two together to basically get a working system on about 5 different platforms rather than just 2. Or you could just use U-boot and have hundreds over hundreds over hundreds of platforms just working out of the box. Guess which one I prefer? Less work is good, right? So comparing the two, Tiano Core is essentially built for closed source environments. Right? It really, you can see it in its genes. It's built in a way that black boxes work just fine. It's built with Windows coding style because the whole idea and everything just came from there's a good reason a lot of developers live in Seattle. Right? Which is good. I mean, don't get me wrong. I like the fact that we do see code that originates from a Windows environment live in the open now. It's a good thing. It just means that it might scare Linux or open source accustomed people. Right? You don't attract too many people into that development that just want to do it in their spare time, because they would have to relearn the way they think or read. And one of the key points that they're thankfully trying to change these days is the build to fork. Tiano Core is really trying to stay core usually, or traditionally is trying to stay core, and is trying to basically make it really hard to have pieces flow back into that core that would enable broader ecosystems. So why would everybody have to re-implement their implementation for a specific driver that happens to live in 5 different platforms, right? But that's the basic thinking. You have core and Tiano Core, and everything else lives on some outside world parts. Which is completely different from the way the typical open source communities work, because we try to pull in everything that we can, so that we can move the whole ecosystem forward going forward. Right? We want to, as a EFI loader, the whole framework here is actually a really good example of this. After implementing EFI loader and putting it into U-boot, we, in one hit, basically enabled 700 boards to run UEFI code, without any one of those maintainers doing any piece of code. They didn't have to worry about it. It just worked. And that's the power of open source in my book, and that's something that Tiano Core is struggling with really hard to basically be inclusive of the ecosystem overall, which actually is something most vendors don't want. I mean, if you're building a server, you don't want to push that code back into some core because you don't care about updating things from that UEFI, the standard UEFI reference implementation, because you ship the server. I mean, it's done. You're off to the next project. You don't want to worry about that project anymore, right? It doesn't get you any revenue in maintaining it. U-boot is monolithic, as I explained earlier, and it's all GPL code, so very copyleft, and it follows the Linux coding style, which makes life easier for people like us that are used to that environment. It makes life harder for Windows developers, so you have something for all worlds, right? But what is that whole EFI framework about that I talked on? So if you look at UEFI interfaces, and this is a really, really simplistic view of it, what you have is basically objects. So you have an object model in U-boot, which is called device model. You have an object model in UEFI world, which I don't think has a name even, but they basically call it protocols and handles. So there are objects in the UEFI world too. And really what we want at the end of the day is to implement drivers and everything in U-boot, but have them exposed via UEFI so that UEFI applications can consume them. And this linking framework, the thing that basically takes U-boot objects and exposes them as UEFI objects, that is called EFI loader in U-boot. And that's the thing this presentation is on. So looking at those two pieces, UEFI and U-boot, when did we actually learn, when did U-boot learn how to speak UEFI? Right. Looking at the timeline, back in 2016, so 2016-05 was the very first version that introduced UEFI compatibility support. So using that version, you could already run Graf just fine on any U-boot version throughout. So anything that ran x86 code, x86 64 U-boot, or ARM U-boot, or ARM 64 U-boot, all of these would just work with UEFI code. So you could just run on any of them, and in most cases it would even succeed to execute UEFI code, which we then really quickly adopted. So as an OpenSUSE contributor, I went ahead and basically enabled a few boards that we do support in OpenSUSE with that support so that we can prototype it in our own ecosystem and just make sure it actually is sane and valid and works. And ever since, we're slowly moving more and more targets over to use the UEFI stack instead. I don't even think there's any target left that still uses our old crafty boot script generator. I hope, Andreas just said that maybe the 32-bit all winners boards still do it. I do hope they don't, but if they do, whatever. They might break eventually. Interestingly enough, the next ones that followed after were OpenBSD. So the very first distribution outside of OpenSUSE that enabled anything with U-boot UEFI support were actually a non-Linux distribution. They were OpenBSD. Because they had the exact same pain points that we had, they just weren't vocal about them. They have the problem that they need a contract to firmware to run, and that contract needs to include block storage access because they need to read their own file system from the bootloader to load their kernel. Well, guess what? That's exactly what UEFI gives you, right? It's exactly the interface level that they need. And quickly after OpenBSD, FreeBSD followed, and both of these are actually active contributors to the EFI support in U-boot these days. So this is a healthy community. A couple months later, we already had Fedora move over to the EFI loader stop, so the U-boot UEFI implementation for 64-bit ARM systems. So 64-bit ARM systems that run with U-boot on Fedora are basically all based on this code now. So if you're booting any Fedora system, that just magically works. The reason it followed so late was that they first had to enable shim support to work. Yeah, Art?
But does Fedora ship U-boot?
So Art is asking whether Fedora is shipping U-boot. Yeah, they are. They are shipping U-boot for specific boards that need U-boot as their firmware to run. An interesting event, in my opinion, happened back in end of 2017 when we grew support to run iPXE. And at first, I was really, really surprised to see that anybody was trying to build to run iPXE. But my impression first was that the guy that submitted the patches for it really just wanted to basically test iPXE. Right? I assumed he was an iPXE developer, and he just wanted to basically have an easier way to prototype iPXE changes. Well, no, not at all. Turns out it was a random hobbyist who still is one of the most active contributors to the EFI loader code, so kudos, who really just had a system, like an ARM machine, a small, whatever, cheapo ARM system back home that he wanted to boot. But turns out he didn't like TFTP boot for security reasons. And so he wanted to do something more sophisticated. He wanted to run iPXE, which as a UEFI application makes use of U-boot's network stack to actually access the network. And that iPXE then can speak iSCSI to mount an iSCSI drive from some other server. So the TCP stack and the iSCSI stack are all implemented in that UEFI code that just comes in as a binary from, well, it is still open source, but it comes in as a binary that runs on EDK2 just as the same as on U-boot. And that iPXE blob then goes and exposes a UEFI block object again. Well, what he also introduced is a conversion layer that basically takes UEFI objects and exposes them again back as U-boot objects. So you can take that U-boot block object and put U-boot's partition table reading code onto it. So now you have multiple sub-objects that basically give you the partitions of that disk drive that is sitting on iSCSI read through iPXE UEFI code that leverages U-boot's core network infrastructure. But on top of that, you can now use U-boot's file system code, which means you can now read a binary from there, like Graf, and boot. So that way, he is booting his system. Yeah, seriously. It took me a long time to understand what his patches were really trying to do. It's just awesome. That's the kind of people you just get with a viable and vivid open source community. He just came along and sent patches. The next thing that happened time-wise is RISC-V support. So I just ran into one of the guys from Endis back at Linaro Connect by accident, and they happened to have upstream code in U-boot, to run basically an emulated platform of their next generation IP they're generating with U-boot, but there's no emulation platform available. So I managed to get hold of one from them and started porting RISC-V code into the EFI loader pieces, which basically was about 50 lines of code, or so, give or take. So it's really just relocation code and a couple of linker scripts, linker changes. So now we're at a point where we basically have conquered the world, almost. But of course, there are a few pieces missing. So what can you expect going forward? One thing you can expect is run the UEFI shell, because why not, right? Actually, there is a really good reason why you want to run the UEFI shell. So who has seen the UEFI shell? Very good. This is an amazing crowd. Usually people don't know the UEFI shell that well. So the really interesting part about the UEFI shell is that it actually was built as part of EDK2 to leverage EDK2 interfaces, right? The whole idea of it was a development tool for EDK2. And now we basically prove the point that having standardized interfaces make it very, very easy and possible to exchange code without necessarily exchanging the underlying implementation. So you only need to work against a standardized interface and you're all happy. And the main reason why we're working so actively on the UEFI shell these days is that we want to run this. That's the SCT. It's some output from SCT. The SCT, I think, Vincent, you correct me if I'm wrong, is the system certification or system compliance test suite? Self-certification, there we go. Self-certification test suite. It basically allows implementers of anything UEFI. So if you're a Lenovo of the world or even an AMI, you run this to verify that your UEFI implementation is adhering to the standard. Well, we should do that same, right? I mean, if we're an official UEFI implementation, we should verify that we're doing exactly the things the spec says we should do. And we do pass a few tests. We've started to pass more during the last couple of months. We're at about 10%, I think. So we're getting there. So eventually we will be an officially acknowledged UEFI implementation that just adheres to the standard. Just if you're wondering why it's why the value is so low, a lot of these checks really just verify whether your input parameter sanitization is correct, right? Do you actually verify that you get a null pointer? Well, it's good to check, but it doesn't actually mean that we don't run normal applications, right? So just because we have a low coverage doesn't mean we don't run whatever is out there today. Again, we actually are running a lot of code already. Another thing that I'm really eager to see going forward, and Simon, if he's around, there he is. Simon actually promised that we're going to take a look at this week, so maybe we'll get there eventually. The Sandbox. Sandbox is a really, really cool feature in U-boot. Because Sandbox basically allows you to build U-boot as a Linux user space application. Now, if you add the whole EFI loader idea to the mix, it means you can run EFI applications basically as Linux applications, right? And that again means that combined with Linux boot means you could potentially I think you're getting the idea. There is one too many layer. I do agree. Maybe we don't even need Sandbox. But the basic, you're getting the basic idea, right? By basically creating a proxy, a really shim proxy layer that just really gives you a UEFI interface without all the other craft that EDK2 gives you, you're suddenly enabling use cases that people didn't think of before. So out of this whole U-boot implementation piece, there's a movement now that people figured, well, maybe we should actually write down what we need from a boot environment so that we can standardize on it, and that's what EBBR is about. So there's a new specification called EBBR, the embedded-based boot requirements. If you've ever heard of SBBR, that's basically the equivalent for servers on ARM. EBBR is a specification that basically says boot using UEFI and device tree and these protocols on an embedded system. Just give me enough interfaces so everybody's happy that wants to run an OS. So it really is a spec to define what boot behavior you would expect from an embedded system. There's a GitHub page. The whole development of that spec is happening fully in the open. I pushed quite hard for that one. It took ARM a while to actually write specs in public. But we are there. So if you want to contribute and you have caveats that you think really should be in that spec, where you're saying, say, I don't know, if we implement secure boot, it needs to be that way. If we implement whatever, you can think of requirements that you would have in your normal experience and everyday life of how booting works. We're more than happy to receive comments on that, and you can just open a GitHub issue to modify the text or send a pull request. It's as easy as that. And EBBR really is all about answering questions. So EBBR basically answers the question of how much of UEFI do I actually need to implement? Because at the end of the day, yes, EBBR basically defines the subset of UEFI that U-boot happens to implement, but it doesn't have to. I mean, it doesn't say you have to use U-boot. You may as well write a proprietary implementation. You may as well use EDK2. You may as well do anything else you want to adhere to EBBR. But from an OS point of view, we can then say we can support your board if you do EBBR. And if you don't do EBBR, come back in a year. Right. It answers the question on how do I deal with variables. Dealing with variables is actually pretty hard if you don't happen to have non-volatile storage that is accessible exclusively to your runtime services with UEFI. It answers questions such as, what if I don't have a real-time clock? There's a real-time a UEFI service that is mandatory that basically says you always have to return the current time of day, day of the year, time of the day, too, all those. If you don't have an RTC, it's really hard to return the time. And how do I combine both firmware and my operating system onto a single piece of storage and have them not interfere, right? Which also is a big requirement in embedded systems, or at least we've seen a lot of requirements there. But server people don't care; they just add another chip. Right? This actually, interesting enough, is a development driven by a good number of companies these days, and contributors and enthusiasts and community in general. So we are getting traction even from hardware people, which is the most amazing part, because they feel the same pain as us. Right? They actually don't want to spend all the effort in enabling every single one, because what's in it for everyone, right? What's in it for us? What's in it, or anyone who does operating systems? Basically, I just couldn't find a nice logo for operating systems. What's in it for people that do hardware? Right? For us, it just basically means we don't have to spend so much effort in getting every single piece of equipment enabled. We just basically can tell people, enable your stuff upstream in Linux, make the DT completely compatible, backwards and forwards, give us a standardized boot environment, and then tell us which pieces we need to enable in our Linux kernel, and we're all set, right? Things should just work. And life really should be as easy as that, and it actually is as easy as that on x86 platforms. ARM is just different. And so we want to basically move it into some sphere where it's easier. It also gives us easy update paths because we don't have to worry about different firmware on different revisions or anything of the likes. We know the interface is always the same, right? It just works. We know that the device tree is the same, even though we do update our kernel version. For hardware people, it basically gives them the exact same promise, just the other way around, right? It means that when they enable EBBR, they can suddenly enable any OS. If they want to start working with one more distro, there you go, right? It just works. If they want to enable FreeBSD, well, they only need to implement the drivers in FreeBSD and don't have to worry about the whole booting stack again. It's small anecdote. A friend of mine worked for Apple back in the day, and he said his one visit to FOSDEM was the weirdest experience he's ever had. There was a room full of hundreds and hundreds of people with a guy giving a 1-hour presentation on how to boot a system. It was mind-boggling. They have half a position assigned to the task. It's one person working half-time on essentially their bootloader, and that's it. Right? They don't give that much thought into booting things up, and we should get down to basically thinking less about it as well, I think. It basically means for hardware people, they have a much easier time to enable us too, right? If we walk over to one more silicon vendor, we don't have to start from the groundworks up on how we can actually eventually start our kernel. We can basically all agree on the same interfaces, and we're happy. Currently, EBBR is at version 0.6. We're expecting version 1.0 to come out this year, plus minus 1 month or so. With that, you probably want to see what it looks like, right? I don't have an amazing demo, depending on how involved you are with, or how much you know how much effort it is to actually get text output in UEFI. But I can show you a demo I'm going to show next week at Connect on bare metal hardware in a virtual machine. So I'm not going to boot up the whole system, but you can basically see its U-boot came up. This is you can see here, this is, there you go, ARM64. This is just an ARM64 virtual machine that runs Graf, and it booted everything from a disk that is passed through using interfaces from U-boot as UEFI interfaces into Graf, and that Graf just works, and that Graf can run your kernel and boot your system, and everything just works. I'm not going to boot the system now because I'm running with QEMU, and it's going to A, drain my battery, and B, not going to finish in a half hour. What I can show you is something that's work in progress. Wait, let me quickly show you the U-boot shell so you know this really is a U-boot environment, right? We are really talking about an original, genuine U-boot environment the way you would expect U-boot to look like. It's just an ARM v8 CPU from U-boot's point of view, and all we do is we basically just call the boot EFI command to execute an EFI binary, but hidden behind a couple of scripts to just find them automatically. And that again shows you Grub, but this time Grub has a nice menu entry where you can actually, well, you can see that it just says chain load this EFI binary, and when you execute it, well, it chain loads the EFI binary, and you can type in there and do things and use the EFI shell the way you would. Ooh, awesome! This is amazing progress in my book because it basically proves that we are now as compatible as we need to run SCT. We are missing, again, one patch set to actually make this reality upstream. I have a branch on GitHub that you can just clone to make this work as well if you want to. But this will eventually just get upstream. We do a couple of things, just see the commands there. So you even have something like SM BIOS view. So you can see that we even expose SM BIOS tables in our UEFI implementation. We do expose the U-boot version in there, for example. So you can see that I'm running current U-boot. We do expose device tree tables. So the whole system just basically flows into the whole U-boot flow and just gives you yet another interface to just make life easy for everyone. With that, any questions? I left out a lot of pieces of the puzzle, so I'm sure I can fill gaps.
Yeah, I have several questions actually. So let us start. So we see here, Vincent, correct me if I'm wrong, you had this already, Astiano core for ARM64, right? You had this implemented as UEFI, Astiano core.
Well, I can just answer that question if you want to. So we actually, as enterprise distribution for ARM, we started off with Tiano core-based implementations.
Yes.
We started from an EDK2 environment, but
ARM64.
on ARM64. So all of that works, and you can use EDK2 just fine. And we actually, if you have the choice between EDK2 and U-boot, and you are undecided which environment you want, and you basically have developers for both, it usually probably is a better choice to take EDK2 because it's more feature complete, right?
This is another question.
But if you come, wait a second, if you come from a U-boot point of view, so if you already have board support packages with U-boot included for your SoC and for your boards for the last 10 years, you're not going to teach those developers how to write EDK2 code. There's no way. It won't work. So that is the migration path for you there.
Yes, but there is big difference between EDK2 and U-boot, which EDK2 is supposed to be the maximum, right? DXC,
Yeah.
like driver, implementation, which will check everything, right? While U-boot will take the minimalistic approach for the drivers, right?
So yes.
Yeah. It barely has any driver, and there's a few of them for standard things in the range that are okay, but most drivers indicate what you can use it.
So Ben mentioned that the drivers are terrible, and one of the nice things about U-boot is that you can mostly just grab Linux drivers and copy them one-on-one, and they basically compile. With some caveats, you basically need to rip out any interrupt code, but the rest is fine. I just did that recently.
Yeah, I see, Ben, that you are liking this more for SIP than EDK2.
It's different things. I mean, as Alex said, EDK2 is originally geared. EDK2 is generally geared as being a reference implementation of the core UEFI. It wasn't, and that it's improving, but it wasn't. And I'm talking from the outside world, but I did port EDK2 to power, so I know a little bit about it. It wasn't really meant to be the implementation that you will run on every board out there. As you mentioned, vendors would use it as a base to do their own implementation, and it was sort of expected that hardware vendors for I/O devices would provide binary drivers for their device, and what is in EDK2 is just basically sample code. It's a bit better than that for standardized hardware interfaces, like some of the USB things. But even then, I mean, practice for various controls out there, you do need to add quirks. So it's, yeah, I mean, and I'm sure since the last time I looked at EDK2, it's gotten better because I know there is an interest in making it better and pushing it more into that inclusive direction. But you're talking about a completely different environment, a different goal, and U-boot in a way is much more driver rich. So yeah, I don't think you need to necessarily oppose them that way. It's they target different people and different environments.
I'm targeting just the time of execution, because U-boot is supposed to be much faster, right?
So the comment was that U-boot is supposed to be faster. Yes and no. It started from the whole idea of being faster and slimmer, and it still is to some extent.
It depends where you spend your time.
So this is about as fast as a normal U-boot environment is, because really at the end of the day, the boot EFI part, the EFI loader framework is just the same level pretty much as any of the other bootloader code in U-boot. So instead of running boot I in U-boot, you just run boot EFI, and you can even pass in a Linux kernel and just boot that directly if you wanted to, if you really wanted to go through the UEFI interface. But that's a completely different topic, because the real point of this is not to be faster or more elegant, or at the end of the day, even the code style. The point is that we're looking at existing ecosystems that currently all do different standards and different ways of things. And UEFI might actually be one of the first promising targets that everybody could just target, even though it's not a great interface. I mean, looking at UEFI and the way things are designed, a couple of decisions could have been more elegantly. But it is one, and it works, and it's there, and it is available. So this way, we essentially extend the reach of the UEFI interfaces.
Yes, you are talking about the UEFI spec.
Yes. take the mic, please.
You're basically here talking about the changing the UEFI spec to be better, right? Because you just
No, I'm
implementing...
talking about implementing the spec.
You're just implementing the spec in the way in U-boot
Yeah.
as it was in EDK2.
The UEFI specification is a monster that defines the entire environment, PI, Dixie, everything. It effectively defines things very deeply, the implementation detail of UEFI. So what is here is a subset of the specification that is mostly at the interfaces between UEFI and the outside world and the applications. And I suppose with the feedback of the driver back into U-boot, you get a bit more than that. But it's not and never will be a complete implementation of the UEFI specification. Again, that's not the goal. The goal, which I understand more as from what we discussed earlier, is really about having a common interface between your firmware, your bootloader, and your operating system. It's not so much about how your firmware is built internally. And the idea is that we have now hundreds and thousands of embedded platforms that exist today that all are built around U-boot. You can just drop that thing in, and those platforms can now put UEFI grub and UEFI interfaces to Linux. This is what it is about. What would interest me is extend that to Linux boot by effectively creating an equivalent thing, or maybe using the same code base, I don't know, I haven't looked at it, to do that from Linux user space as well.
Yes, definitely.
And so instead of binding onto Linux drivers, U-boot drivers, we bind onto Linux user space interfaces to drivers. It's a little bit difficult to run UEFI drivers in user space.
You don't need to usually. So most of the pieces we care about don't include Dixie at all. We don't usually provide Dixies.
No, the case you gave with iSCSI might be a little bit more tricky. But
the iSCSI one even works for most of part, because the iSCSI one just only adds the interface inside the container you're currently running in.
Yeah, we could probably do user block device.
That would work from user space just.
But yeah. But anyway, and the point is we could extend possibly this to Linux boost as well. So in that context, it's about, and that's probably what EBBR is basically. This is a subset of the UEFI specification that is of interest as an interface between low-level initialization firmware and a bootloader and operating system. Yeah.
Let us just try to compile. I did not finish, please. So this is the lightweight, the lightweight kind of UEFI, using like subset of the spec.
How small can you get an EDK2 code base?
I have no idea. So what I'm saying here, you are trying actually to adopt UEFI to all these devices you had before.
Yes.
Right? Like a lightweight.
And new ones. And new ones too. If people choose to base their development model around U-boot because they happen to get U-boot developers easier. Look at the presentation from the Facebook guys. Their main problem with traditional firmware is they don't get firmware developers. They have Linux developers. They want to write Linux code. Right? U-boot is the closest you can get with a non-Linux environment. Not closest, Barebox is even closer, but it's very close to a Linux environment with non-Linux code.
Okay, so now the question is about this. So what you presented to us should be merged, right?
It is merged. It's been upstream for 2 years. Yes, please, thank you. And that code, the timeline you looked at were the points in time when code got merged, not when anything appeared randomly. This is actually upstream code for the last 2 years in U-boot. If you have any...
Also the UEFI shell, right?
The UEFI shell is not upstream yet because I didn't list it in the timeline. But let's take that offline. Yes, we have another minute.
So I'm very interested in the sandbox application and the capabilities of running this under Linux. As Ben mentioned, as a possible way for Linux boot to be able to make use of Dixie modules.
Me too. That's exactly why I pushed for the fact that we want to make that whole sandbox target actually execute real-life binaries. We don't want to just have it as a test bed. It should be running real UEFI binaries. Yes.
Can you talk briefly about how the device drivers are mapped in, or how that's implemented?
We just, in Sandbox, we simply match to the U-boot Sandbox device drivers, and the person you want to talk to sits right there because he's the Sandbox maintainer. So he knows exactly how all the Sandbox drivers get mapped to host drivers. Basically, it really just maps into normal Linux user space glibc callbacks, essentially, for reads and writes on disks, and for network. I don't even know what he does, but it does work.
And do you have boot services support, or only runtime services?
Only boot services.
Only boot services.
Only boot services at this point. So for runtime services, we basically need two things. For boot services, we need to, for runtime services, we need to do two things. For runtime services, we need to, implement some way in Linux to basically change kexec so that kexec becomes UEFI aware, so that you can take a UEFI blob that got loaded from user space, push it down via kexec, and then execute that with the UEFI calling convention and additional tables that you have and additional pieces of code. And the other thing you need to do is you need to teach the UEFI spec that maybe there are no runtime services. and
Very nice.
Well, not deprecate them, basically just allow every call from a runtime service to return, I'm not there. And that's exactly what I talked to Vincent about yesterday, and he's in violent agreement. So we're probably just going to go and change the spec and make runtime services essentially optional.
Changing the spec.
Yes. Awesome. Any last minute? Yes.
I do believe that some parts of kexec are already somewhat EFI aware, so...
They are EFI aware of passing through the EFI parts you were booted from into the payload, and I think that even only works properly for ARM and not for x86 or something.
Yeah,
there were some caveats.
It's somewhat broken, but...
But this is different. This is about basically you come in from a non-EFI environment and you want to ignite a new EFI environment to the next kernel you're loading with your own intrinsics.
Yeah.
Or semantics. Well then, thanks a lot.